we go. Now, as you're reading through the first part of your D1 notes here, you'll probably recognize some of the wording because we're basically going to walk through that document that you just did together. We're going to work on it again, just with a different number, to practice it a little bit. So this standard, at the end of it, the goal is that you can give a thorough definition for a derivative and that you can demonstrate whether you know a function is increasing or decreasing using a table and or a graph. 4-type problems is that you'd be able to explain the difference between instantaneous and average rates of change and giving examples of both kind, and that you can explain the connection between limits and derivatives. So that's the goal at the end of this, but we're going to just touch on the basic foundational things today. So this is the same door example, same picture you saw before. I don't know if they specifically asked these questions, but the questions we're going to answer here are: at any particular instant in time, is the door opening or closing, and what tells us if it's opening or closing, and how fast is it moving? We can answer this question graphically and numerically. Okay, so suppose the door is pushed open at 0 and ends or slams shut again at 7, so we're looking at the same door you were looking at before. So is the function the same as the one you did before? Sure. So our function, I don't know if, we're going to label it with the same variables here. I'm going to write it in function notation. D of t equals 200t times 2 to the negative t. That's going to be helpful because you should already have this function in your calculator. But on that worksheet, what focal t value were you focused around? 1. So now we're focusing around 3 and to see where our differences are. All right, so what is this question asking for? There's a few words that you'll notice as we talk about derivatives and integrals that jump out or should jump out. One phrase that's a very key phrase is this phrase, how fast. So this question is asking for a rate of change. You know it's asking for a rate of change because of that phrase, how fast. Like if you're driving and I ask you how fast you're going, what would be your answer? A typical answer. Miles per hour. Something miles per hour. 45 miles per hour, 80 miles per hour, whatever you're going. Miles per hour, if you were to write that out, it'd be miles on the top of a fraction over hours. So this would be an example of that because we have time at the bottom of our fraction here and some variable on the top. So we need a rate of change. How fast? And we're looking at a specific instant at t equals 3. Is the rate of change or how fast the door is opening or closing, is it going to be different at 3 than it was at 2, than it was at 1? Yes. Because a door doesn't, even one that automatically opens like the ones with the handicap button that you can push on the way in, it doesn't open at the very same exact rate as it closes, right? It kind of opens more quickly. There's even like a little jerk at the beginning because it opens and then kind of opens the rest of the way. And then it closes slowly. So it's not going to be constant. And when anything changes like that, it's not a constant rate of increase or a constant rate of decrease. You have a function that looks something like this. Instead of, if something's constantly growing at the same rate or decreasing at the same rate, that's always a linear function, right? So we are not dealing with a linear, but we're still talking about rate of change. Up to this point, we've not ever really talked about rate of change in terms of other graphs or functions besides linear. I'll wait to mention that until later. All right, so average rates of change closer and closer to 3. I think Okay, let me ask this question. Can I find the exact degree that the door is opened when time is 3? How do I find that? Plug it in, because isn't my function the degrees in terms of time? So if I want to see how many degrees it's opened at a specific time, I would plug in 3. Let's go ahead and do that. Since your function's already in your calculator, you would just use your table. And when you plug in 3, what do you get? 75. It might even be on your worksheet already. Good. All right. So at time equals 3, D is 75 degrees. Does that tell me anything about how fast it's going at that point? No. Is it still moving at 3 seconds? Yeah, because it's not 7, so the door hasn't shut yet, so it is still moving. But yeah, it's open 75 degrees. When you're looking at rate of change, in terms of a graph here, rate of change technically is slope. But I don't have a line here, so it's not like I can solve for m in this function. I can't get this into y equals mx plus b because it's not a linear function. So in this case, when we talk about rate of change, we're talking about the slope of a curve. Okay. Does anybody have the graph on their calculator right now? Or a good graph? Okay. So if you have the graph on your calculator, I want you to see what happens when I pick a point to zoom in on. Well, actually, let's trace. I'm going to get pretty close to 3 here. And I'm going to zoom in. Okay, again, I'm going to trace. Okay, I'm at the same point, so I'm going to zoom in again. Okay, that's a pretty good graph. Now, if I'm zoomed in pretty far here. What does that graph look like on the screen? It looks like a line. Is this graph a line? No. But this is what we call linearizing, yes, I'm saying that right. Linearizing a function, where you don't have a line, but when you zoom into points that are really, really close to the point you're looking at, it ends up kind of looking like a line. So we can find the rate of change, or we can find the slope of the curve by narrowing in just on that point. So instead of looking at the whole thing and picking 2 random points off the whole curve, you're going to pick 2 points that are really, really close to the value that you're looking for, which you've already done with 1. Like, what are some of the points that you used around 1 when you were finding rates of change? 1.1, 1.001, those kind of sound like what we did with limits. 2, you pick values that are really, really close. That's what we're doing, though, is we're linearizing the function so that we can actually find the slope. Okay. Something else to include here with rate of change is that you're looking for how much something changes, or in this case, the change in your degrees over the change in your time in this specific example here. Alright, so I'm going to find some values first. Oops. Yeah, this is time, this is D. And I'm going to focus around 3. So let's look at 3, 3.1, 3.01, and 3.001. So you should just be able to plug these into your calculator. I'm sorry, Heather, I show yours. You can plug in 3, you should get 75 because we already figured that one out. 3.1, you get 72.31. 3.01, 74.73. 3.001, 74.973. Okay. Now, to find average rates of change, that means we're going to have to figure out some fractions here. And they're all going to be change in degrees over change in time. And we're going to get closer and closer and closer. So the first one I'm going to find is the change, or the average rate of change between these 2 values. 3 and 3.1 are pretty close together. But let's find the slope between these 2 points and see what the rate of change is. I always do final minus initial, but you can go, this is the same concept of, does it matter what point goes on top? It doesn't. So you can put this y value first and subtract this one, or vice versa. I just always keep it final minus initial. So the bigger value here, or sorry, the final minus initial. The initial point that you're referencing is the point at 3. So 72.31 minus 7.5, 3.1 minus 3. But again, we could switch these up and we're going to end up with the same answer, so it doesn't really matter what order you put them in. Okay, so the average rate of change here, don't just depend on me to do it. Make sure you're trying to punch out yourself. Now, if you're putting it all in your calculator, just make sure that when you divide, make sure to include that all in parentheses, otherwise your answer is going to be off. Did you get negative 26.9? That's what you should get. Okay, and then we're going to go one step closer, so I'm going to go with 3.01 and 3. Now, why do you always have to use the 3? Like, why can't I go set 3.01 and 3.1? Yeah. Well, it's what you're focusing on, right? You want to know the instantaneous rate of change or the estimate of it at 3, so we need to make sure we're still focusing on 3. We're just using values that are getting closer and closer to 3. So, 74.73 minus 75 divided by... Did you get negative 27? Okay. And then here, 74.973 minus 75, 3.00. Now, out of all these choices, which one is going to be the most accurate? The last one. Which for the last one, I end up getting negative 27 again. So if I had to estimate what the instantaneous rate of change is at 3, what would I estimate it as? Okay, so negative 27 what? Degrees per second. Now, what did you get as your estimate on that worksheet? At 1. Negative 30. What does the negative tell you?
The direction.
That the what is decreasing? The degrees. Because time can't be decreasing, right? Because time is always ticking forward. So your degrees are decreasing, which means, is the door opening or closing?
Closing.
It's got to be closing, right? Because when you're opening, the degrees are increasing. When you're closing, the degrees are decreasing. So what this tells us a lot about the situation. It tells you how fast the door is going at that instant, or the estimate of how fast it's going at that instant. But it also tells you that the door is closing. This is actually a little bit of D2 as well. I mean, we use it to introduce derivatives, but there's not a ton more to it. No. Okay, for the door example, the angle is said to be a function of what? The angle, the degrees, is a function of what? You can't have degrees unless there's some time ticking, right? If there's no time going on, then the door is neither opening nor closing, so you can't really have degree there. All right, time is the what type of variable? You have 2 types, independent, dependent. Which one is it?
Independent.
This is the independent. Time is always independent of everything because time doesn't care what's going on around it. So time is, I won't say always, but pretty much always your x values or your independent variable. And the angle then would be our dependent. Okay. These names make sense because nothing starts or stops time until December 21st, 2012. And angle, and the angle cannot increase unless time has passed. If time has not passed, then the door can't open, and therefore the angle is not going to change. The instantaneous rate of change of the dependent variable is said to be the limit of the average rates as the time interval gets closer to zero. Okay, what this means here, time interval gets closer to zero. What's the time interval between 3.1 and 3? What's the space between 3.1 and 3? How many seconds? 0.1. Okay, then between 3.01 and 3 it's 0.01, and then here it's 0.001. Okay, which number is smaller? 0.001, right? And then if we kept getting smaller, so like this idea is saying as this time interval gets closer to zero, because 0.01 is a pretty small space between those two numbers, and you can keep getting smaller and smaller and smaller and smaller, right? Will you ever reach 3? What happens if you reach 3? What if this becomes 3? You're at the bottom, and then the equation explodes, right? So it can't work. We're done. But could I get really, really, really close to 0 down here? Yes, I could. It's that whole concept when we started talking about limits, and I was walking towards the door, and I said, will I ever reach the door? No, but can I get really, really close? Yes. So same kind of idea here. But that's why it's called the limit, because these values, as that time interval decreases to 0, or as it gets closer and closer to 0, the space between those two numbers, this is going to get more and more accurate. So just like when you were looking at the limits and you were testing values really close to the one you were looking at, same thing with average rates of change. The limiting value here is called the derivative of the dependent variable with respect to the independent variable. Now, that term with respect, you'll start to hear more and more with derivatives because it shows a relationship between the two variables. So with respect means finding the change in y as your change in x increases or decreases. It's basically the way that in calculus they show the relationship between y and x, which means, like if I said, find the derivative with respect to length, that means the length is your x, and then whatever the other variable you're looking at is your y. So the with respect means it's telling you what your x is, because in a lot of derivative stuff that we do later on, you just have two variables, you don't know which is the independent or dependent without that phrase. So keep that in mind. It's kind of comparing. It's telling you what depends on the other. It's like y with respect to x means y depends on what x is doing to figure out the derivative. All right, so we just found average rates of change of f of x over an interval of x values and use these to estimate the instantaneous rate of change at a particular value of x. That's really wordy, but we can't find the instantaneous rate of change right now because we cannot plug in 3 here. Instant means at the instant of 3. So there's no adding or subtracting. It's just how fast is it going at 3. But we can't plug 3 into this. So we just have to estimate, and this is how we estimate. Eventually we'll come across some rules that allow us to find the instantaneous without having to estimate anything. Okay, so definition of derivative. We'll be adding to this as we introduce other things, but the derivative of f of x at a particular x, so this is kind of the same wording we use with limits, C just represents your focal x that you're looking at, is the instantaneous rate of change at x equals c. So when you're talking about the derivative is the instantaneous rate of change. What we're doing in this section and in D2 is we are estimating the instantaneous rate. We're not actually finding the instantaneous rate yet. Okay. We'll add to it after we do some more problems here. Okay, go ahead and flip. Okay, I believe mark these both with a 4. We'll come back to these because these are both part of the 4-tech problems that you're able to explain these differences and these connections. We'll come back to that when we're ready for it. All right, for example 1, this is one thing that you have to do for this standard. At each marked value, so you see how it's like marked there at A, marked there at B, you have to state whether the function is increasing or decreasing, or neither, as x increases from left to right. And then you're also supposed to state if the increase or decrease is fast or slow. Okay, so we're going to do these 3 together, and then you'll get more practice on that today. So we're going to start with point A. Now, at point A, are you increasing or decreasing there? I'm increasing. Now, with a graph, it's kind of easy to tell because your graph is sloping upward, so we can say it's increasing. So A, f of x is increasing. Now, we also have to say if it's increasing quickly or slowly. Now, when you're looking at it, I'm going to zoom in here. When you're looking at it, you do have to look just right there at that point. And I always like to draw in a tangent line. Now, tangent is not the same. You probably talked about this in geometry, but when you're talking about a tangent line, like if you're looking at a circle, a line tangent to that circle is a line that just touches once. Okay? It's not really the same tangent as in SOHCAHTOA. So when you're looking at a curve like this, I like to draw a tangent line that kind of follows the slope of the curve. Just kind of sketch one in there, because I can tell better from the slope of a line whether it's going quickly or slowly. Is that a shallow line or a steep line? It's more shallow, so you would say f of x is increasing slowly. Okay, the rate of change is not fast there because we have a tangent line there that is pretty shallow. Now, if we look at B, is f of x increasing or decreasing? Still increasing, right? So f of x is increasing. And if I drew in a tangent line, and I want you to practice drawing these tangent lines in because we have to use them for another thing too. So when I draw that in, is that a pretty steep line or a shallow line? Steep. So we would say quickly, increasing quickly, because rate of change is pretty fast there. Okay. How about you do this one on your own? There's 4 points there to look at. So A, B, C, and D. Drawing your tangent line. And all you have to say is whether it's increasing or decreasing quickly or slowly. I'm calling for you to give me your answers, so just make sure you're ready. Okay, Nate, why don't you start us off with A? What did you say for A?
Fast increasing.
It's increasing, and then how quickly is it moving, or slowly?
Fast.
It's fast. Good. So this should be increasing quickly. All right. Emily, what about for B?
Increasing slowly.
Good. Increasing slowly. And if you drew in your tangent line, which I do want you to practice, it would look something like that, because it's following the slope of the curve. Let's go with Zach. What did you say for C?
Decreasing slowly.
Decreasing slowly. Good. And if you drew in your tangent line there, it would look something like that. A shallow line there. And then for D, let's go with Michaela. What did you say? Increasing quickly. Good. Okay. Yeah, this is going to. Do this one. I think we're catching on to this. Fine. And I should zoom out a little bit. I'll call 4 more of you. All right. Selena, give me A.
Alphabet increasing quickly.
Good. Increasing quickly. Sierra, B.
X increasing slowly.
Okay, this is a tricky one. It kind of looks like it's increasing, but it also kind of looks like that graph has done what?
Flatline.
It's flatlined. It's kind of plateaued. That's actually what that point is called. It's called a plateau point. So, good job. So for B, when it kind of looks like it's bottom out like that, what do you think the slope is?
0.
It kind of is really close to 0. So we would say at this point that that is a part of the graph where you're not changing. Rate of change has stopped increasing or decreasing. So what would the rate of change be? 0. So I think the option we could say was neither. So this is neither increasing or decreasing. And so there's not really much we can say about it, because we can't say it's moving quickly or slowly, because we've just kind of bottomed out there. Neither increasing quickly or, yeah, neither increasing or decreasing. For C, Heather, what'd you get?
Alphabet increasing quickly.
Good. Increasing quickly. And then Ben, last one.
The different effect was increasing slowly.
Good. So you're still increasing there, but increasing slowly. What if I put a point right there?
Where?
Right there.
Should be
Right next to D.
neither.
It'd be neither. Because this is like the graph for, let me flip back to this graph here. That's like this point on our door problem. What's happening at that point in this scenario?
Transitioning from opening to closing.
It's transitioning from opening and closing. So like when you open up the door, it's that like point where it's kind of just there right before it starts to close again. So it kind of hangs out for a second and then starts closing. So that is our transition point, the maximum degrees that it would be open before it started decreasing again. Okay, I think we're going to go to, just so we get some more practice of this, because I want to make sure that we don't lose it for tomorrow. Go to example 3. Depending on how long it takes us, because it's almost 2:30, we might be able to talk about this before you leave today, but I want you to pair up with somebody close to you. And by pair up, I mean like actually just you two working on it. This is very similar to the door problem that we've been doing, just with a different function, but the setup is kind of the same. What's the focal point that you're looking at? as you glance through that problem? What's the T that they want you to focus on?
0.
No.
It's greater than 0.
This is just telling you that your graph is going to be for time values that are greater than 0. 5. You're looking at a focal point of 5 in this problem. Okay, but you're kind of setting it up the same way, so I want you to practice with that person that you're close with, or close to. Are we good?
That is.
Okay,
Indeed.
move around if you need to. Separate yourself a little bit. So we will be talking about this one, but I want to give you a head start on it and see how far you can get on your own.